Hello, everyone. Welcome to our Tuesday, January 22nd live session. My name is Matthew. I'm one of the instructors for our online courses. We are grateful to have you here today. It's a cold and strangely snowy day here in Tucson. I'm going to hand this over to Professor Impey, and then we'll get started with your questions. Please post those in the chat and just ask them once. I grab all the questions from the chat and we see them. So just ask them once and we'll get them there.
Okay, welcome everyone to another Q&A session for the online classes. I'm ready to take your questions.
Excellent. The first question is from Edward Ruel, who would like to know if what you think about the Harvard astrophysicist Avi Loeb new idea that Oumuamua might be of alien, meaning extraterrestrial intelligence origin.
Yeah, this is a big subject in astronomical circles. It's a bit of a controversial book. So Avi Loeb, who's very highly esteemed astrophysicist, a theorist, he's the chair of the astronomy department at Harvard and has written lots of good papers on cosmology. He wrote a paper a couple of years ago noting that Oumuamua, the sort of interloper from outside the solar system that had an extremely strange shape for an asteroid, for example, highly elongated, had orbital elements, particularly speed and trajectory, that suggested it was truly an interloper from extraterrestrial origin, that it had an artificial origin. And he's now turned that into a whole book, claiming this is the first contact essentially with intelligent aliens through an artifact that they've sent in our direction. And the gist of his argument is based on the trajectory and the speed of the object when it was observed near the Earth. And the fact that that suggests that it may be operating like a solar sail. And in fact, so it's not like a big rock in space, it's actually extremely thin and wide and long, and was designed to harness radiation from its original star or maybe our star to move around. And it's an alien artifact. It's controversial. He's taken a lot of flack for this. I mean, he's a smart guy, so he has marshaled some arguments, not in favor of the alien hypothesis. He has no evidence that aliens created this thing or sent it our way, but just in the sense of trying to show that it has aspects of its trajectory this can't simply be explained by any other hypothesis. So that's where it sort of sits. And even that's been disputed. So other astronomers are pushing back and they're saying that he doesn't really have the evidence to claim that this could not be caused by natural phenomena. He doesn't have direct evidence that it's as thin as he claims it is and therefore is acting like a solar sail. And there are even some holes in the solar sail hypothesis as far as its trajectory and speed goes. So the whole thing is up in the air. And I would say the consensus, of course, among astronomers is the more conservative or conventional interpretation that it's a naturally occurring object with a very strange trajectory, for sure, but that you don't have to invoke alien intelligence. That's a bit of a stretch, and you have to be very confident to invoke that hypothesis. So I'll just leave it there because I don't think it's truly resolved. Sometimes astronomers have to be comfortable with a little uncertainty. We can't always resolve things. And I'll reference in this story Tabby Star, which was a subject of heavy discussion in astronomical circles and on this Q&A session a couple of years ago, a star where the eclipse pattern showed very striking and dramatic changes that were not typical of exoplanets that we know about. And again, it was speculated that this was evidence of artificial structures around the star built by alien intelligence, and so that this was another alien artifact that we thought originally was an exoplanet. Well, natural interpretations for Tabby stars, a very strange light curve, have emerged, and you don't have to jump to the alien artifact hypothesis. So if I was going to place a bet, I'd say that Oumuamua is in this category and that we'll eventually have a conventional explanation.
Thank you very much. The next question is from Chris Matson. What are your thoughts on the possibility of microbial life on the moons Titan and Enceladus? Do you think these moons should be the focus of our search for life?
They're very different cases, so I'll take each one in turn. Microbial life on Enceladus, it's completely possible. Enceladus is a very small moon of Saturn, which, to great surprise of astronomers and planetary scientists, was found to have icy jets, geysers that were pumping out what had been liquid water straight into the vacuum space, where it turns into small icy particles. And this was observed by the Cassini probe that was in Saturn's vicinity for over a decade. And eventually Cassini actually flew through the plumes and sniffed them and showed that this was remnants of a salty subsurface ocean, or lake if you like, on Enceladus, this small moon. Very surprising. Enceladus had to have an internal energy source. It's not big enough to create geological heating sufficient to keep liquid water so far from the sun. Remember, we're at the distance of Saturn here. So far beyond the habitable zone in a conventional sense. But it is subject to strong tidal forces from Saturn, and the tidal heating is sufficient to create interior volcanism and liquid water. So we understand how liquid water could exist under the surface of Enceladus and then squirt out through gaps or fissures in the rocky surface. If there's internal energy and liquid water and carbon-rich material, which we're also certain there is, then you have all the ingredients needed for microbial life. The question becomes, with the ingredients all there, the chemical ingredients and the liquid water medium in which life on Earth first developed, do you have enough time, and is the environment there stable enough for the processes to occur whereby simple chemicals connect to form the first cell? We don't know how long that took on the Earth, but it probably took tens of millions and maybe 100 million years or more on the Earth. And we don't know if Enceladus has had a stable subterranean environment for that long. So it's highly uncertain whether there could be microbial life really on Enceladus, but it's certainly possible in principle, so we should absolutely go look. As far as microbial life on Titan, that's a different issue, and I'll address it separately because Titan's a very different planetary object. It's a large moon of Saturn rather than a very small moon of Saturn. Titan has sufficient surface gravity that its pressure of its atmosphere at the base is twice the pressure of the Earth's atmosphere, and it's made of mostly the same thing, nitrogen. In Titan's case, almost exclusively nitrogen, so there's no oxygen component. There are other small trace gases there. So Titan is shrouded by a fairly thick atmosphere. Its surface temperature is very low, well below the freezing point of water, and so the liquid lakes on Titan, and just recent work, recent radar work that was published just a month ago, showed that at least one of these lakes is at least a kilometer deep. So these are substantial bodies of liquid. The liquid is ethane methane. It's liquid forms of ethane methane mixed with a little bit of ammonia and probably a little bit of liquid water in that. Those lakes get some modest heating from interior because Titan's a large moon. It has geological activity. It has cryovolcanism underneath its lakes, and so there's energy coming up into the liquid from below, which will raise its temperature substantially, perhaps to the temperature that's familiar on the Earth. And the question of life is an interesting one because this is a different environment for life. This is not the same ingredients that were on the Earth when life formed, which is essentially water and then carbon-rich material and silicon-rich material dissolving in the water, and then molecules gradually combining to become more complex. We don't know if it's possible to have an alien and bizarre form of biochemistry in a medium that's ethane and methane as opposed to liquid water, which it'll also have some other basic rocky material dissolved into it. So there'll be some of the same simple chemical ingredients that Earth had, but very different proportions, and it's a very different situation, and it is a lot colder. So it's a matter for complete speculation whether there could be microbes on Titan. But what biologists or biochemists almost certainly think is that if it is life, if there's life there of any kind, it's a very different form of life. The templating molecule may not be anything like RNA or DNA. The biochemical network that gets set up in this medium is going to be very different from what happened on the early Earth. And so life there will be version 2.0, something very different from what we have on the Earth, which makes it a really fascinating and, to me, compelling target for future exploration. So scientists are planning missions to go back to Titan. Remember, we only had half an hour of data from the Huygens probe that landed there, launched by Cassini in 1995, very long time ago. Well, there's a Dragonfly mission on the books with NASA, which will actually use drone technology essentially to go to Titan. It'll take another decade before it gets there, and it'll hover around the surface and sample the liquid in a number of these lakes and do chemical analysis. That would be an enormous step forward in our understanding of Titan. I'm not sure those missions are designed to detect life directly, but it'll get us some way along that road.
Excellent, thank you. The next question is from Vishnak Harish, who's on with us live. When will the Giant Magellan Telescope start working?
The Giant Magellan Telescope is, the big project we have at the University of Arizona. We made the mirrors for that telescope, and we're 10% partners in it. It's an international collaboration. It's destined to go to Las Campanas Observatory in Chile. The mountaintop's been scraped. They're starting to put metal down and concrete down. And like I said, most of the mirrors have been done and polished. It's hard to tell when first light will come. This is essentially a $1 billion project, and I would say so far the partners have raised about 800 million, maybe 750 million, which is enough for what we call first light capability. The first light would take the flower petal design, where 8.4 meter mirrors are arranged like petals around a central element, and the minimum configuration would be the central element plus 3 of the 6 surrounding petals, so 4 mirrors out of 7. And the first light for that probably will be 2024, late 2024, maybe early 2025. Now that's still a very substantial telescope, and you at first light with 4 mirrors rather than 7 will be able to do a substantial amount of the science that the Giant Magellan Telescope is designed for. And sniffing the planets, exoplanet atmospheres for signs of life is probably one of the most compelling projects on the books for that telescope. So we're all very hopeful that it's about 4 years off.
Excellent, thank you very much. The next question is from Nisha Macy. Do you think there were ever people living on the other planets in our solar system?
Well, that's an interesting question. And by people, I presume you mean other species, other alien creatures, and other alien life forms, not humans. I don't think humans, there's an interesting idea, of course, in history. It's a fringe idea in academic history, that humans have not monotonically and smoothly evolved from being primitive hunter-gatherers towards the technology and civilization and space travel we have now. There's the idea that humans long ago had higher capabilities, including technology, maybe the ability to leave their planet, and then subsequently lost all that and then had to rebuild it again. I don't really think there's any evidence for that. So then the question becomes, has the solar system ever been occupied, inhabited, or visited by alien life forms, alien intelligent life forms? And that again is a fringe proposition, because most astronomers don't believe there's any compelling evidence of intelligent life out there. SETI has not had any success in looking for it that way. Most astronomers discount the nominal evidence of UFO sightings as being alien visitations, just because there's just not enough physical evidence that anyone can examine and that's compellingly pointing to alien artifacts. And we've seen no instance on our exploration with space probes of the planets of the solar system that they've been inhabited, had their terrains altered, that there are artifacts left behind by some previous life forms that may have long since disappeared. There's no evidence for that. So no, I don't actually think the solar system has been occupied before humans occupied it on our planet.
Next question is from Kokila Harini. Is it possible that we could travel to another universe or other universes?
That's an interesting proposition. I guess the first question to ask or answer is, what is the likelihood there are other universes? The multiverse idea emerges from modern cosmology, from the quantum genesis of the universe, to include the possibility, maybe even the plausibility, that there are other space-times distinct from our own, and these would essentially be functioning as parallel or separate universes that have their own evolution and possibly their own physical properties different from the properties in this universe. So the multiverse idea is out there in cosmology. It has not been tested, and so no one has ever shown that there are other space-times or other universes. It's just a concept, a hypothesis. There's very minimal indirect evidence to support it in the inflationary idea. And then if it were the case that there were other space-times, the question of travel to those other space-times is a whole different matter. As we know, travel even between stars for us is beyond the pale. We're unlikely to be able to do it for centuries, even with projected technology. So we have trouble traveling the tiniest distance in our own galaxy, let alone to other galaxies, let alone to other space-times. And of course, if a space-time and a parallel universe was distinct from us as indeed a space-time, then there may be no conceivable communication between those universes in terms of electromagnetic radiation, which means by definition there would be no possible travel between those universes by spacecraft.
The next question is from one of our live participants. Nicholas from Athens, Greece, asks, how can we combine the second law of thermodynamics with Newton's and Einstein's reversible time in cosmology terms?
Well, the idea of time and its reversibility in the universe is still an object that's an active discussion on that, both at the philosophical level and at the physical level, and in terms of the theories of cosmology. So the laws of thermodynamics that are indeed, they're sort of overarching principles that apply to physics as we understand it in the laboratory, and everything we've studied so far do point to a time arrow based on the principle of entropy and its universal increase. The tendency towards disorder is essentially, at the microscopic level, a tendency for complex systems to evolve to the most probable states. And the most probable states for a set of physical objects is, of course, a jumbled or disordered state, and that's where the idea of entropy comes from. So this times arrow from thermodynamic principles seems to be fairly well understood, and we can see examples of it in the universe in terms of how stars are perhaps creating heavy elements in their cores, but in the end they're increasing entropy and increasing disorder because they're gradually radiating away their heat that came from the ordering of atomic nuclei into waste energy or heat out into interstellar space, where it dissipates and leads to disorder. So we think this is a very strong principle. In cosmology, it's not clear how this principle applies. What cosmologists would say is that the initial conditions of the universe, as far as we can determine them, which were in the situation of the Big Bang, require an unusually low degree of entropy. So running the Big Bang backwards, running the clock backwards on the universe, points to a situation of relatively low entropy compared to how high the entropy could have been. And that, in fact, may be part of the reason why in our universe time's arrow manifests, because the initial condition, for whatever reason, it's an initial condition, we don't have a premise for why the Big Bang was the way it was, had low entropy, and so we would then expect to see that entropy increase on average in the universe as a whole. So I think the cosmic entropy idea and time's arrow are actually connected fairly directly to the idea of thermodynamics and the increasing entropy in more localized situations.
The next question is from Jim McLeod. Which professional publication is, quote, the cat's meow for an astronomer to have his or her research shared with their peers?
That's a good question. The main astronomical journal that has the highest citations and prestige is the Astrophysical Journal, APJ, as it's called by astronomers. It's published by the American Astronomical Society through the Institute of Physics, and it's been in existence for well over a century, I think 130 years or something like that. So the Astrophysical Journal is the preeminent journal. It has a supplement series which can take papers that have large amounts of data or simulations or catalogs, and it's grown rapidly over the years as astronomy has grown. Outside of the astronomical literature, the preeminent journal is Nature. So Nature, of course, is a journal that runs across science. It has a very complex peer review system where every article is reviewed by, I think, 4 or 5 separate layers of review or independent reviewers. It's quite extensive because in a normal paper in astronomy you get one referee. If you don't like the outcome, you can appeal and possibly get a second referee, but basically you have to deal with one. to get into Nature, you have to run the gauntlet of multiple referees, and so it's harder, and so Nature is viewed as a hard journal to get into, and of course space is shared with very hot fields like genomics and so on, and Astronomy gets its fair share of articles. So those are the two journals that are preeminent for astronomers.
The next question is from Sandeep Reddy. Could you please comment on why the surface temperature on the sun is relatively low compared with the rest of the sun?
Well, the sun is a hot ball of plasma. It's not really a gas, it's a plasma because the temperature is so high that electrons are not attached to protons. It's a neutral. It's electrically neutral, so there are an equal number of protons and electrons. So basically, when you collapse a large cloud of a gas and form a star, the center of the star triggers ignition of fusion reactions, and the fusion reactions generate energy release, and that energy release exerts pressure which keeps the star puffed up, if you like, to a size, in the case of the sun, 1,000,000 kilometers or so. So it's an equilibrium situation called hydrostatic equilibrium, where at every point within the volume of the sun there's a balance between the gravity force inwards and the pressure force outwards, and the source of the pressure force is radiation from fusion. So as you move out through the sun, and that balance is always maintained, the equilibrium temperature goes down. In the fusion core of the sun, the temperature is at the very center of the sun, it's about 15 million Kelvin. At the edge of the fusion zone of hydrogen to helium, it's about 10 million. And as you move out, the temperature goes down until you get to a point that we see as the surface of the sun, the photosphere. And that's the point at which the density of this plasma lowers to the point where photons no longer scatter off electrons. Electron scattering is the primary process for photons not traveling in straight lines in the middle of the sun, which is why we can't see into it. The surface or photosphere is the place at which the density is low enough that those photons can travel freely. And so we, looking back, see it as an edge. And so the sun appears to have an edge, even though it's not a discontinuity in either temperature, pressure, or density. And so the sun's temperature is just gradually declining as you move further out. And when you work out what is the temperature at which that holds, where a photon will no longer interact or scatter with an electron, it's about 5,800 Kelvin. And so that's the temperature of the sun as we see it. And for a black body or a thermal object, at that temperature, the peak of the radiation is in orange-yellow light, and that's the color of the sun as we see it.
The next question is from Jaya Apendran. Is it really going to be possible in the near future to travel to space for a common person? And when do you think that might be able to happen?
I think it's about 10 years away for everyday people, not necessarily poor people, but middle-class people, to travel into space. So we see signs of it happening all around. SpaceX has had enormous success now doing contracts for NASA that have let it develop its rockets and its capabilities. SpaceX recently took American astronauts to the space station, first time that American astronauts had been launched by an American technology into Earth orbit since the demise of the shuttle 10 years ago. And so SpaceX now has the launch capacity to take astronauts into orbit, and its long game is clearly to take civilians into orbit with the same rockets. And what will they do there? Well, they will either have a sort of joyride, maybe 1 or 2 orbits around the Earth, and then come down sort of like the very first astronauts did, so a few-hour experience, or because it's also, there are parallel processes to get sort of little space motels or hotels. Robert Bigelow is the famous billionaire who's behind a lot of this stuff. At some point you'll be able to have a vacation in space. I don't think civilians will be able to stay in the International Space Station, but there'll be alternative accommodations if you like. So these plans are in play, and I think it'll be another 5 to 7 years before civilians are going up in significant numbers. Price tag initially will be high. It'll be millions of dollars. I don't know how many, maybe a couple of million. Meanwhile, Richard Branson is back on track with Virgin Galactic to do his suborbital flights. These barely get to the formal definition of space. They do not nearly get to Earth orbit, so not as high at all, more like 100 kilometers up, rather than 200 or 300 kilometers up for Earth orbit. And he will be charging a lower price, more like $250,000, maybe $300,000. And he was derailed by a fatal accident a couple of years ago with his prototype Spaceship Two. But I think they've solved those issues, and he should start flights again next year, maybe late this year, and will take paying customers within a few years. So by 10 years from now, I think the first wave of space tourists will have been up, both from Virgin Galactic and SpaceX, and the price will start to come down, and it'll start to move into the arena of everyday people.
The next question is from Kenneth Wally, who asks, what is the importance of finding water on the moon?
Yes, the moon is not a very easy place to live. And so there are plans for returning to the moon, just to visit and do what we did there in the late 60s and early 70s, do some geology, do some exploration. But there are longer-term views of having a colony there, either a renewable colony where astronauts come and go every few years, or maybe even a permanent colony where the colonists live and die there. So that's on the cards. The moon would be a base for industrial activity in the solar system. It would be a launching point for other missions, things like mining asteroids, things like humans going to the outer solar system. The moon is a good staging point because its gravity is weak, and it takes far less rocket fuel to leave the moon than it does to leave the Earth. So that's why the moon is central for future exploration of the solar system. And why water is important is for the obvious reason that if you have water, it just minimizes the amount of stuff, the sheer weight. Remember how heavy water is. Every kilo of water, every gallon of water that you have to lift off the Earth's surface to take to the moon is at a significant cost of rocket fuel. And so you clearly want to be able to live off the land, so to speak. You want to be able to use the water that's already there. And so people have paid a lot of attention recently to where the water on the moon might be. We know there's modest amounts of water all over the moon, and in the shadowed lips of some deep craters, there's substantial amounts of water. And at the lunar poles, in the sort of more semi-permanently shadowed regions, there are substantial ice deposits, maybe as thick as glaciers, hundreds of meters deep. That's not the best place for a moon base, however. So it's almost certainly going to use mining the water from under the soil and separating it out. So why is water important? Well, it's actually important for 3 reasons. Water is important, of course, to drink, and if you wanted to do hydroponic farming or gardening or create crops on the moon, the soil is impossible on its own. You'd have to create a habitat, and you'd need water. So water for living. Water can be fairly easily electrochemically separated into hydrogen and oxygen. And with the oxygen, of course, you have a vital element for breathing, your air. And with the hydrogen, you have a vital element for rocket fuel. So you can create fuel, breathable air, and water to live on if you find water on the moon, and it does exist. So it's a very good and important sign that we found water on the moon, because it makes the likelihood of a lunar base in the next few decades much higher.
Aditya Chowdhury would like to know, and I don't know if this is related to the recent tweet that Elon Musk posted, but he was talking about carbon capture technology. But Aditya would like to know, is capturing and storing carbon-based gases possible or not? And are there current technologies for capturing carbon dioxide here on Earth?
Yes, there are definitely carbon capturing technologies. In fact, there are power stations already in the United States and elsewhere that have carbon capture operating on their smokestacks on the places where the carbon dioxide would otherwise be entering the atmosphere. So there are various pure chemical and some electrochemical methods for capturing carbon dioxide. And sometimes in the end it gets liquefied or solidified and as a way of being removed from the system. They're not very cost effective, however. At this point, it's a marginal benefit over just reducing the carbon dioxide emissions itself. So you can scrub carbon dioxide out of an emission of a power station, for example. You can capture it for other uses, or you could emit less of it in the first place. And at this point, it's cheaper with various other technologies to emit less of it in the first place, or not to use mechanisms like coal-fired power stations or oil-fired power stations, which emit so much carbon dioxide. So it's not clear whether the best approach is just going to be to move away from heavy carbon dioxide emitting power generation mechanisms, or try and capture it. And it would have to be very cost effective to do that, because power is really quite cheap now worldwide.
The next question is from one of our live participants. Dan Cooper would like to know, if Titan has ethane or methane lakes, wouldn't it be highly explosive?
That's a good question. And yes, the answer is, with the right ingredients, yes, it would be. The vital missing ingredient that would make it extremely explosive is oxygen, of course. The explosive recombination of ethane and methane with oxygen, because when you explosively combine any hydrogen-rich molecule with pure oxygen, you of course release a lot of energy, and the byproduct is sometimes water, there's nothing harmful about water, but it's an explosive reaction. So on its own, in terms of what we think is on Titan, it's not explosive. If you just lit a match on Titan or had a flamethrower or something like that, you wouldn't cause a conflagration. There's a little acetylene on Titan too, and that's clearly a highly flammable molecule, but it's very small amount. It's a trace element. So Titan is not flammable as far as we know.
All right, the next question is from Nisha Macy. How long would it take to travel from Earth to Mars?
It sort of depends on how much energy you want to use to do this. Now, if you just look at the orbits, you might imagine that the easiest, cheapest, and shortest way to get to Mars is when we're as close to Mars as we get in our orbits. Remember, Mars is at 1.5 astronomical units, and so it's essentially 50 million miles to get to Mars at its closest approach. But in terms of orbital dynamics and the relative motions of these objects, that's not how you're going to do it, of course. If you just launch straight towards Mars out from the Earth, Mars will have moved forward in its orbit. So you have to have a more complicated trajectory. And it turns out that the best orbital trajectory and the fastest way to get to Mars with current technology takes about 8 months. And that uses a significant amount of energy. There are other trajectories which use less rocket fuel, less energy, and they take up to a year or even a year and a half, I think. But 8 months is the fastest you can do it. And definitely for for space probes where you don't really care, you can use the lower energy orbits and trajectories that take longer. For humans going to Mars, where the radiation environment in space is so hazardous, you want to make the journey as short as possible. So 8 months would be the answer.
The next question is from Stephen Smith. With technology racing on, is the window for interstellar communication rather short, tens of years before our methods become outdated?
Well, that's always a concern, because we do what we can, right, with the technology that we have. Seth Shostak, who's a chief scientist at the SETI Institute, sort of likes to say, when he's asked, well, why do this experiment? Because the technology is going to get better in the future. Like, why not just wait till you have better, more efficient technology? And he says, well, you've got to do the experiment you can. People didn't say to Christopher Columbus or an explorer like Magellan, well, you could try going around the world or going halfway around the world with these small galleons and ships, and it will take years. Or you could just wait to have a jumbo jet, and then you can do it in a few hours. Well, okay, you could wait hundreds of years to a new technology, but you need to do the experiment you can do. And it's the same issue with interstellar communication. Indeed, it may be that in 100 years, we decide that sending gravitational waves, because we know how to do that, is much easier, more efficient, and is what any sophisticated or advanced civilization would do. And sending radio waves or pulsed optical laser pulses, is so old-fashioned and retro and inefficient. But in the end, you do what you can with the technology you have, and as new technologies develop, you move on to those. So it's true that there is a kind of windowing of technology on interstellar communication, which involves the various assumptions about technology and how it will develop. And you're going to be blind, of course, to technologies that you don't yet have. But that's the limitation of the experiment, so you just have to decide that the experiment is worth doing given those limitations.
The next question, the next question, I will briefly mention that Irene asked, what do we think of the evidence that Oumuamua was an object projectile from the outer solar system? Now, we did address that earlier, but I wanted to give you a chance to just say hello to Irene and kind of do a short recap.
Sure. Hey, Irene. Good to have you on. Oumuamua is a controversial object because we don't really understand its motion and orbit. And so the new book, which I haven't read yet, I read the technical article that Avi Loeb wrote with a collaborator 2 years ago. That's the basis of the book, really. He's taken that idea and turned it into a full book. I think his first contact with intelligent alien life. So he's pushing an idea that I don't think is fully supported by the data. He's being provocative deliberately. That sort of fits his personality, actually, because I've met him a few times. A very smart guy, very esteemed astrophysicist, no doubt, and a big conventional body of data and publications in cosmology, basically. So this is a new area for him. But he's smart, and he knows that the orbit of this object is very difficult to explain under conventional interpretations. But the trouble is, we just don't know enough about that object to know whether a conventional interpretation fails. For instance, although it is clearly very elongated, Loeb, in his solar sail hypothesis, is speculating that it's extremely thin. So in a third dimension, it may only be millimeters thick, just like a solar sail. And we simply don't know that. We have not measured its three-dimensional geometry well enough, nor the density of the material it's made of well enough to know if it's been constructed artificially like an object or if it's just a natural rock in space that has a very unusual shape. And we also don't know that geophysically you couldn't generate an object with Oumuamua's shape naturally. So he's pushing a hypothesis that's fascinating, that he can justify at some level, but the truth is we're just not knowledgeable enough about Oumuamua as an object to decide between these propositions. And so in those situations, scientists tend to be conservative because the radical, outrageous, wild hypotheses often turn out not to be justified. And so the bulk of his colleagues, I'm staying agnostic, but the bulk of his colleagues have pretty much decided that it's not an alien artifact.
The next question is from Anayansi HR, who would like to know, is there relative movement between galaxies, kind of like planets, rotation and translation, and how quickly it changes and if that can be calculated?
Sure, galaxies are moving relative to each other. We can only measure the radial component of that motion using spectroscopy, and that's of course primarily the expanding universe. So the radial velocity of most galaxies is a reflection of the expansion of the universe. So we measure that, but we can infer three-dimensional velocities because when we see galaxies in one region of space, for example, in a cluster, so almost a spherical distribution of galaxies, then even though the radial component is all we can measure, it's one of the three dimensions of the motion, by understanding that the object is part of a spherical system held together by gravity, we can infer its true spatial velocity. So we can use inference to predict or project or infer the 3D spatial velocities of many galaxies. And their motions are caused by a combination of two things. They're caused by the expansion of the universe. That's the fundamental imprint of expanding space-time that carries galaxies away from each other. And then the second component is called, in astronomy, historical terminology, it's called their peculiar velocity. And it's basically the difference in their measured radial velocity from the the velocity you would infer from a smooth expansion of the universe, so-called Hubble flow. And the reason it's not always just the Hubble flow number is that the objects are gravitating and attracting each other. And so galaxies deviate from simple Hubble flow, from the smooth expansion rate of the universe, by gravitational interaction. And so that is the peculiar velocity, and we can measure that because we know what the Hubble flow velocity should be at any distance from a smooth expansion of the universe. And then there are galaxies that are bound to each other. Milky Way and Andromeda are moving towards each other at 100 kilometers per second and are going to pass each other in a few billion years and then merge into a giant combined galaxy. So many galaxies have motions towards each other that indicate interaction or eventual merger. And that's not, of course, what an expanding universe would predict. That's caused entirely by the gravity of the objects acting on each other.
Our next question is from meow, who's on with us live. Are there medications or drugs that can help humans to do better in space?
Apart from Dramamine, no. That's a good question. Yes, there are medications, there are standard medications that astronauts have taken, especially those on the International Space Station. I mean, the obvious ones are, calcium supplements and various more sophisticated compounds that alleviate bone loss, because astronauts spending significant time in zero gravity suffer muscle atrophy, bone loss, distortion of the visual field caused by pressure buildup in the eye. That's an unpleasant one. It has led to some vision problems in astronauts, and I have not heard of any drug that can alleviate that. So those are the big ones to avoid the degradation of the physical body from zero gravity. The other one, of course, deals with the disorientation of zero gravity and space sickness, basically. When NASA eventually revealed the statistics, they kept it secret for a while because it was not consistent with the right stuff to think that astronauts got sick and couldn't do their job. And essentially, from the first few programs, the Mercury, Gemini, and Apollo programs, about 10% of astronauts got severely ill in space or space sickness, and a good fraction of those 10% were debilitated enough they couldn't function. They essentially became dead weight in their spacecraft. That's not a good thing. And apart from what most people would know of as the patch, the thing that many people have taken when they go on sea voyages and so on, they can use the patch. Scopolamine, I think, is the active ingredient. Dramamine, of course. But I think they have side effects. They make you drowsy, and so most of the motion sickness drugs that I know of have side effects that are not consistent with being sharp as an astronaut and doing your job. So they try not to administer those unless someone's really having a problem. And many astronauts have no problem. It's disorienting, the zero gravity, but they get used to it and they don't need any drugs.
The next question is from Red Unleasher, who's on with us live. Can you tell us if dark matter is influenced by the Higgs boson or vice versa? And yeah, that's it.
So the relationship between dark matter and the Higgs boson is very unclear, mostly because we don't know what the dark matter particle is. If the dark matter particle is what people still think it might be, which is the lowest mass supersymmetric stable particle. The supersymmetry idea is a unification theory of physics that hypothesizes shadow particles, the distinction between bosons and fermions, integer spin and half integer spin particles, is wiped away with supersymmetry, and you end up with a shadow set of particles. Many of these will be unstable and massive and hard to see except in an accelerator. But in all these theories, there's a stable supersymmetric particle. Usually it's called the neutralino in the standard supersymmetry theories. And that has the properties of dark matter. It has about the mass, and there's abundant enough that it could explain the dark matter. So that's what people think. The relationship to the Higgs is indirect. A neutralino, if that is the dark matter particle, will not directly interact with the Higgs, but the mass of that particle, a massive particle to represent the dark matter of the universe, is imputed by the Higgs mechanism. So we know that a neutralino, just like any other dark matter particle, if it's a fundamental particle, will gain its large mass by essentially a viscosity effect in the Higgs field. That is the field that we think permeates space by which particles get their mass attributes. That's the Higgs mechanism, and that's the Higgs field. So there is a connection, just in the same way there's a connection for any fundamental particle to explain its mass.
The next question is from Pratyush. Can you tell us why it is that we are receiving signals from other worlds? I think this is from the news that I saw another article about the signal, the radio signal from Proxima Centauri, I believe. But if you can talk about the latest information on that.
Yeah. I don't think there's anything really new in terms of fully understanding it. Again, it's not a situation that leads automatically to any sense of a alien intelligence at work or an alien force behind this signal. It seems like it will be a natural phenomena in the end. There are a number of radio signals that have remained mysterious that we still struggle to understand. For example, fast radio bursts have been puzzling for several years, and just very recently there's now a direct inference that associates fast radio bursts with magnetars, that is, highly magnetically intense neutron stars. So the Proxima Centauri radio signals are, again, likely to have a conventional interpretation that we just don't fully understand at the moment. And there are at least 6 or 7 research teams working pretty hard on this.
The next question is from Ali Bar. If someday we discovered intelligent life on a planet outside of our solar system, should we land on that planet and introduce ourselves? What's your opinion on that?
I think if we learn of the existence of an intelligent species or creatures in another star system, the idea of eventually having a visit or having a reconnoiter in space is not a bad one, because through the communication we will presumably understand the nature of these creatures, their intentions, their capabilities, their intelligence, their culture if they have culture. So I think since you're going to have communication first, the idea of having direct contact later is not unreasonable. If you learn things that make you suspicious or skeptical, then of course you would never want to have that contact. You also might worry, of course, as we would with pathogens on living planets that don't involve intelligence, just microbial worlds out in space. You also might worry that these might be hazardous to us. It's a great H.G. Wells story, of course, classic science fiction, War of the Worlds, that the Martians come and are in the end incapacitated and killed not by our superior technology, because we're losing, but by pathogens that they can't handle. And the same might be true if we go to visit aliens on another world, or even a world inhabited by microbes. So I think the biggest danger of contact might actually be sort of the pathogen response or pathogen situation rather than malintent and war and destruction. But that's all very speculative, since we haven't made any contact yet so far.
The next question, Oscar Reina Garcia asks, could music be a universal fingerprint for intelligent civilizations, as in art-making human civilizations?
Well, that's an interesting speculation. In the first order, we're looking for signals that imply artificial origins or intelligence behind them. So we think we know what natural signals are in the universe. I mean, routine metronomic, sort of cyclic or periodic signals are not signs of intelligence. So it has to be information coded in the signal, however it comes, from radio waves or optical waves or whatever. Now, the distinction between information coded in a signal and music is a little arbitrary, because there are all sorts of artificial signals that convey intelligence or some intelligent force behind them. They don't have to be music. Music is a very particular thing, because it's particular because it requires a certain atmosphere. It's based on sound waves traveling through a medium like air, and that may not be true for an alien world. And it's also, of course, depends on culture. So music or bird song, whale song, there are examples of what we might call music used by other intelligent or moderately intelligent creatures on the Earth, but not really in the same way that we use music to express emotion and feeling and to communicate in a more profound way. So yes, if we were able to discern the likelihood that some alien entity is sending us what we would describe as music, then that would be extremely exciting. However, I think realistically that's a very unlikely outcome, because we would have to know so much about the alien behind the signal to infer all that goes with making music. Now, we sent music into space, of course. The record, the gold-plated record, playing at a half long playing records, rotations per minute, is out there in interstellar space now, attached to the Voyager spacecraft. So we've sent music into space as encoded in an analog form on a gold record. Will an alien pick that up and understand it and know what the music encoded on it is? I don't know. Just like the reverse experiment, I don't know either.
The next question is, there are several people who would like to know if you think that NASA will be able to launch the James Webb Space Telescope by the end of the year.
NASA is clinging still to a launch in October, I think, this year. The preparatory work has been going on. The integrated assembly of telescope and instruments is sitting at a NASA center, undergoing its final thermal vacuum and shake test and so on. Remember, there was a bad outcome on a shake test last year, and that set the project back a significant amount. That led to the most recent delay. It's definitely in a mode where there's a huge resistance to any further delay, and most of the instruments and most of the telescope assembly and most of the telescope is just ready to go. There's also a launch window issue that they don't want to use a delay for that reason, and the cost issue is paramount because James Webb has blown through its budget cap a number of times and is now in excess of $10 billion and counting, and so Congress is going to be very unhappy if there's another delay. So altogether, I think, yes, we can still bet on a launch this year for that telescope.
Excellent, thank you. The next question is from Soham Das. Do we have any kind of defense for avoiding or stopping a massive asteroid crashing into the surface of Earth? And if so, what are they, and how successful might these methods be?
Yeah, we have a pretty good defense. The first stage of the defense is, of course, knowing what's out there and how it's approaching us or not. And so the network of telescopes that Congress actually insisted that NASA build to detect anything larger than, I think, 270 meters across, which is a regionally Earth-destroying object. That's complete, and so we have cataloged essentially almost all the objects larger than about 250 meters across. Now, smaller than that, you can still cause a big problem, and the inventory is much less complete, down to 150 or 100 meters across. But we have a pretty good idea of what's out there. And these objects are being monitored at distances of hundreds of millions or billions of miles. So we actually, given their orbital speeds and their speeds in space, would have warning of several years for any object that approached the Earth. The second phase of the protection is computers. So to know that something is going to hit you, you actually have to know its trajectory and its orbital path very accurately. And that's not known for most of these objects. We just pick up the ones that are no threat to us at all, and then identify the subset that are on potentially Earth-crossing orbits. For that subset, you then watch them more closely, observe them more frequently, and apply computers to their trajectories to predict their paths more accurately in the future. And only then, if one really appears to be on an impact trajectory with the Earth, do you kick into gear your prevention strategy. So you've already got two phases to go through. And the truth is, almost nothing gets to the stage of attention after that second phase. Most objects just will not be coming close enough to the Earth, or will be a near mass. Space is big and these objects are small. The final step and the remedy is, again, given a couple of years lead time, which is what you'd have, you could prepare an object, a rocket, and we have the technology to do this. We've reconnoitered with comets and asteroids with space probes and landed on them, so we know how to do this. We would reconnoiter with the object with a space probe, a pretty massive space probe actually, land on it and tether to it, and then you could use the rockets of the space probe pointing back out into space to adjust the trajectory of the object. You essentially kick it to the side. You can give it a transverse pulse or impetus of energy using rockets attached to something tethered to it to change its course. And if you do that far enough away from the Earth, you actually only need a small incremental change in its transverse velocity to let it miss the planet comfortably, easily. So that would be the strategy, and we do have the capability to do that with some great confidence, actually.
There are two sort of related questions. Petra Pinter and Dylan Anderson have questions about gravitational change if different objects disappeared. So we'll start off with Petra's question, which is what would happen to gravity and the orbit of planets if the sun disappeared?
Right. Well, if the sun disappeared, just vanished and its mass vanished, of course, that's what counts really, if it's orbits, then each of the planets and all the objects that are in the solar system would continue with their instantaneous trajectories they had at the moment the sun disappeared. So the Earth and all the other planets, of course, are in nearly circular orbits around the sun, and they have a transverse velocity in their circular orbit. And at the moment the sun disappeared, they just continue with that orbital velocity in a straight line, and whatever straight line they were pointing in at the instant the sun disappeared. And so they would just all fly off into space. And since the planets would be at different places in their orbital paths, not all lined up with each other, they'd all fly off in different directions. So the solar system, and this would apply to the asteroids and the asteroid belt and everything that's bound in the solar system, including the comet cloud far out, they would just all scatter out into space in different and randomly different directions. So the solar system would essentially dissipate into interstellar space.
The related question from Dylan is, what would happen if the moon exploded?
That's an interesting question. If the moon exploded, it's not going to happen. The moon is a pretty stable object. It's completely, non-geologically active, so there's no volcanism, there's no external agent I can imagine that would cause the moon to disrupt or disappear or explode. But if the moon did explode and the pieces just flew away from the current situation and essentially left the Earth orbit, then that would have an interesting effect on the Earth. First of all, we would lose tides, so the Earth would no longer have tides. Second of all, of course, we'd no longer have eclipses, so that would be gone. It all depended on the particular distance of the moon relative to the sun and their similar angular size in the sky. And the third and maybe most profound effect that wouldn't manifest for a while is that the Earth's orbital tilt would become unstable. So the Earth's orbital tilt, which leads to the seasons of 23.5 degrees, is stabilized essentially by the relatively large moon. Mars, with no large moon and a similar orbital tilt, has a historical variation in that tilt of tens of degrees. And the Earth's orbital tilt would start to meander or move without a moon too, and that would lead to the seasons on the Earth either potentially becoming much stronger or potentially going away if the orbital tilt went towards zero.
All right, so this is probably our second to the last question. We have a question from Soham Das, and I have a personal interest in this question. There was an interesting article about using artificial intelligence or machine learning to find gravitational lenses in data that otherwise we would not have found. So can you talk about how we use gravitational lensing in order to observe distant stars and how we're finding more of these gravitational lenses?
Yeah, gravitational lensing is a very widespread phenomenon now in astronomy. It's a sort of pretty routine tool, actually. We see lensing on different scales. We see large-scale lensing caused by galaxies acting on other galaxies, and that sometimes produces multiple images, like with a cluster of galaxies lensing distant galaxies, or just a slight shear in the galaxies just distorting their images, and that has to be detected statistically. There's also microlensing, where you don't actually see multiple image formation or actual distortion, where the light of an object varies because a dark object passes in front of another object and there's a momentary amplification of the light. The role of machine learning in this is important because some of the signatures of microlensing or any kind of lensing are quite subtle. There's subtle distortions in the shape of a galaxy that are really only detectable statistically. Or if it's strong lensing, it's a very rare situation. It's a needle in a haystack experiment. Essentially, on average, about 1 in 100,000 galaxies is directly and strongly lensed by an intervening galaxy. That's a pretty rare occurrence. So you have to have statistical techniques to pull it out. And so machine learning is powerful in this regard because you can let the machine learning train on the known instances of gravitational lensing, and we have hundreds or now thousands of examples, and then you can unleash it on large data sets where it's looking, having been trained, the neural net having been trained on a known set of gravitational lenses and their full variation, it's able to dig them out of a vast data set very efficiently, and better, of course, than any human could. So it's a very good and powerful use of machine learning in astronomy now.
So there's the final question for today is going to be about time, and there's been a discussion in the chat about, I think there was an article recently about reducing a minute being reduced to 59 seconds, and the year was shortened by 19 milliseconds. I think what they're referring to is that there was recently a leap second or something like that that was added to the calendar. Can you talk about what leap seconds are, how those work, and how they're decided, we decide to add or take away time from a day or from a calendar?
Right. Well, I mean, for average civilian timekeeping, leap seconds simply don't matter. I mean, it's a second in a year is a tiny fraction of a percent of the year, and so it really doesn't matter for operational purposes. But because we have systems like GPS, which depend on very accurate timekeeping, that's the way we know our position on the Earth in civilian technology, we actually do need to keep accurate time, and astronomers keep very accurate time. And the issue of leap seconds arises because of the variation in the Earth's orbit around the Sun. If you're tethering your time to either a day, which is the spin of the Earth through one cycle, or a year, which is the motion of the Earth once around the Sun, these are not fixed quantities. The Earth's rotation period is actually changing very slowly over time, and it varies by a significant amount because the Earth is not a spherical object, for example. And the Earth's orbit over the Sun is, of course, varying with position in the orbit because we have an elliptical orbit, and it's also varying over long periods of time. And so the leap second was an artifact just made to reconcile the equation of time, which is the variation in the time kept as the Earth moved around the Sun, and we travel through one solar year, with the day, which is the spin rate of the Earth, which defines most of our working on the Earth's surface. And to reconcile those two, occasionally you have to insert a leap second, and this happened recently, and it'll happen again in the future. And it's really esoteric in a sense because there's very few parts of civilian life that depend on this, except that one example of GPS, which we all depend on. So that's the last question, and thanks for that. All varied and interesting questions today. We'll announce the next two sessions soon, and meanwhile, keep looking up. It won't work here because it's snowing in Tucson, which is very unusual. We'll see you in a week. And thanks to Matthew for facilitating.